Hello and welcome to tutorial 3 of the course Reinforcement Learning offered via NPTEL. I am Avik Kaur, PMRF PhD Fellow at Indian Institute of Science in the Department of EC. So today we'll go through some bandit algorithms. So topics of today. Gradient based RTM bandit algorithm. Then we revisit MDPs. And alongside, we'll introduce infinite horizon MDPs. In specific, to be specific, we'll only discuss gamma discounted infinite horizon MDPs, and then we'll coding of dynamic programming. Well, let us start then. So a map is can be written as a tuple of the action set and a mean reward functions, right? So at every time, just a second. Okay, so someone is saying that he cannot join this meeting. Have you, any one of you, ever experienced such things? Yeah. Yeah. Sorry for the interruption. So the agent collects reward RT upon pulling arm AT at time t, and the expectation of RT given AT equals to A is mu of A. Okay, so we have this mu A, which is expected reward of arm A. So we have seen how to estimate of mu A. We are denoting that by mu hat T A, where T is basically at certain time, what is the estimate. So that is sum of rewards from time 1 to t, t minus 1, etc. Because at t we have not pulled arm at yet. So whatever reward we have gathered together, but only when we have pulled arm A, right? So indicator at equals to A. So indicator at equals to A means it will take value 1 when at equals to A, it will take value 0 when it is not. By total number of pull of arm A, that is sum of indicator at equals to A. So uh, you'll do that. Uh, say this is the horizon. Uh, at time t equals to t1, you have a set of mu hat t1, the set of estimate for all A in the action set. I'm assuming that you have finite action set. And at time t equals to t1 plus 1, you have the estimates t1 plus 1 A. But you have only updated one arm, and that is 80. So here you have pulled arm 80, and only mu hat T80 will be updated. So here you have uh, done an incremental algorithm, right? Uh, so is it covered, this incremental algorithm? And can you remember that? Anyone? So basically what you need to do in this step is you need to update mu t plus 1, 50, update mu t plus 1 hat AT from mu T hat AT. Yeah, so can anyone of you please tell me how to do that?
Is the current average plus a fraction of difference between the current reward and the current average.
Okay, so we can write mu hat T plus 1 T as let's not write AT here. Just T equal is equals to 1 to T RT indicator A. Sorry, this is S. RS times AS, and A is equals to A. And is equals to 1 to T indicator AS equals to A. So this is generic. I'm doing it for all A. Now, one thing is indicator A T equals to A equals to 1. And this is one option. And another option is that is equals to 0. Still is equals to 0. So if it is 0, then there will be no change. You can understand that easily. If it is 1, there will be some changes, and that we can write as some incremental algorithm. So we can separate out s equals to 1 to T minus 1. And the other term. Here also same. S equals to 1 to T minus 1. So B, AS equals to A plus indicator AS equals, sorry, AT equals to A. So from now on, we are considering only the case 1. So case 2 is unnecessary to uh, discuss. Case 1. Also, we denote this variable, this sum is equals to 1 to T minus 1 indicator A is equals to A. So this is the number of times we have pulled arm A until time T, T excluded. So is equals to 1 to T minus 1 S indicator K is to A. So now we are considering it equals to A. So we'll just write RT by NT A plus 1. Okay, so now we have to write this as so this we had, right? So mu hat T A, this we know, right? Can anyone of you tell what is that expression? Anyone? Okay, so let me write. So if you want to bring, yeah, sure. Do you have question? Okay, so if you want to bring NDA and this first term, I mean, we need to separate this term and this term. So what you will do? You will bring out this denominator entirely from this expression and multiply, apply, and divide by NTA. So what you do is, and you will write this, and then you have to divide it by NTA. This is clear, right? Someone is saying something. Okay, Yash, I think, yeah, I muted you. If you have some question, you unmute yourself and ask. Okay, so the first term inside the bracket is mu hat TA. So we have got NTA, T, plus 1, mu hat TA plus RT. So is it, I think there's something wrong because, oh, so there has to be one by NTA here, right? Better not to write the second term like that. So can write the second term as R, sorry, plus RT by NTA plus. So what we can do is we can write this as mu hat TA minus 1 by NTA plus 1 mu hat TA minus RT. So this is your incremental update of the estimate of the mean reward. So that simplifies the algorithm and decreases the compute complexity for sure. And you have, I think already this is also covered for non-stationary bandits. Uh, you take some instead of NTA uh, dividing with number of times you are pulling the arm, you multiply with some less than one constant, some alpha. So that makes more sense for non-stationary problem because you outweigh the previous rewards. So that is something like so where you update new hat t plus 1 a as new hat t a minus alpha. And this is when at equals to a. And you don't update if not. Right. So these two different things you have there. And then you have studied UCB, you have studied epsilon GD, you have studied Thomson sampling. And then in last week, you have studied reinforce or some gradient-based bandit algorithm. So let us do a recap of gradient-based bandit algorithms. So I have a question. I mean, uh, do you prefer if if I do coding of gradient-based algorithm, or you want to try on yourself? Okay. Okay, so I'll try it today itself. But the thing is, I have not coded it yet, so I have to code it here and with your help. So yeah, that may take some time. Okay, so here the idea is your policy. Policy means where by which you are choosing your action, probability distribution on the action space. That is your policy at time t. So what is policy in this case? So policy we have studied in context of MDPs, but that is not what we are discussing here. So here policy doesn't depend on state because there is no state at all. So without depending on the state, you are just saying that at this time we'll choose action based on some distribution. So that distribution is your policy. That doesn't depend on any. That is not a function of any state. So policy is a distribution on action set. Okay. So we'll denote policy by pi a, and at time t we'll denote it by so sorry, we will denote it by pi, and a action a is chosen according to pi. So yeah, and you have also, I guess, studied parameterized policy. So parameterization. So here pi is parameterized by some parameter vector, or can be one element that is a scalar, some parameter vector pi theta, and this is again a distribution. So one example of such parameterization I'm giving now. So this is called Boltzmann parameterization. I think double N, right? I'm not sure. Uh, yeah, I think double N. Boltzmann parameterization. So this I think you have seen somewhere, at least if you are exposed to neural network, there it is used a lot. So phi, so theta is a vector in theta is a vector in R. Action set is assumed to be finite. So if there are this arm set is 1, 2, 3, then for example theta is basically theta 1, uh, theta 2, theta 3, and it belongs to R3. So, and there is a temperature parameter. This temperature parameter, this term came from physics. So in physics, these things are used. It is denoted by some t is taken. So let's call it some alpha. So temperature parameter is just something fixed. You can take it as one. So, okay, so for the time being, let's take it alpha, but we can replace it by one while coding. So pi theta a. So that is a probability mass, right? At a, what is the probability we are taking uh, actioning? So that is e raised to uh, alpha theta by sorry, theta a. Theta a is the corresponding parameter plus sum of b in. So a is already written, so writing b to denote arm, e raised to alpha theta b, right? So this is normalizing. So this is indeed a probability. Uh, so if you see this pi theta 1, pi theta 2, pi theta 3, then this is indeed a probability mass function. This is a PMF. I mean, this is a valid PMF. That's what I mean. Why? Because the sum of A belongs to A, pi theta A equals to 1, and all pi theta A greater than equals to 0 for all A. So this is a valid parameterization, but the thing is, when you lay some algorithm, you have to uh, you don't know theta A, theta what your value of theta A, theta B will be. So for the ideal case, if you know the which particular arm is the base term, there you will take, say, base term is best arm is A star. Then option 1 is take theta A star. There are lots of options. Sure. So theta A star equals to infinity, positive infinity. So, and very large. Let us not write infinity. That will create some mathematical problem. Take theta A star, very large, and theta A for all A that belongs to this action space, but except theta star. I think you are familiar with these notations, right? Set notations. If not, then please stop me and I'll clarify. So theta A for, yeah, in theta A equals to something very small. Uh, Straight small die. And I don't know what it's mean by near infinity, but it is not a valid um, mathematical object near infinity. But I guess what you understand what I mean. And option 2 is take theta A star uh, finite and theta A for all A belongs to action space, but not equals to A star. To be near negative infinity. So that will make it very large. Make e raised to alpha theta A star large, and pi theta A star will be close to 1. And pi theta A for all other A will be close to 0 for all A comes to A on A star. So you can verify that for the second case also the same thing will happen. So the idea is when you are starting, you do not know which arm is the best. So initially you will put your policy will be to try all the arms, and eventually when you will be more sure about which arms are better, you will put more probability on those uh, those arms, right? So when you will know that your certain arms are performing better than other arms, it's simple. When put high probability on better performing arms. Better performing this, how do you understand arm is performing better? Simple, that is mu hat T A is larger in comparison to others. So Boltzmann parameterization, how we can use in this context is the following. So at time t, we keep parameter theta t, and theta t a equals to e to the power alpha theta t a by e to the power alpha theta t b sum over b. The idea is very simple. Take theta t a to b equals to mu hat t a. That's it. Very simple idea, right? So that is, I'm saying just one possibility that if a arm is performing better, you just take uh, that arm, put more weightage to that arm. But this may not be grounded in some theoretical thing, right? So to do that, we'll do certain analysis. So this is one option. May not be grounded in theory. So we'll assume that this theta t a is some function. We'll update that function. I mean, we'll do some analysis and try to see what theta t will make more sense. Right? So whatever theta t is, uh, what do we want? We want to increase so expectation RT, expectation with respect to pi theta uh, for some theta, which is mu a sum over a times pi theta a. That is our expected reward at time t, right? I think we are denoting it by small r. And this expectation is uh, based on the function, based on the policy pi theta, and pi theta is directly controlled by the parameter theta. So expectation, this expectation is basically controlled by theta. So this is our objective. We want to maximize this. We want to maximize this. So I guess you all have studied stochastic gradient descent or gradient descent algorithm. So what you do there, you have a parameter theta t. So in the context of neural network, the neural network weights and biases are your parameter. So you update your parameter. That is, you go from theta t to theta t plus 1 by taking a step towards the gradient. So if you want to minimize loss, then you take negative of the gradient. If you want to maximize objective, uh, here in this case we are maximizing, so we go towards the gradient. So gradient uh, taken on theta t. Better to write gradient taken on theta a mu at sorry mu a phi theta a evaluated at theta equals to theta t. So if we simplify this, you can take this gradient inside the summation, and mu a doesn't depend on theta. So only pi theta will depend on it. And you can write so this we can uh, now we can change this pi theta so separately. Delta yeah, pi theta t. So pi theta a we have what is pi theta a? E raised to alpha theta a by so summation mm, e raised to alpha theta. Sorry, here is no t step theta a and theta b. So if you are familiar with uh, multivariable calculus, you'll know that say theta equals to theta 1 and theta 2, then gradient theta some function of theta is basically equals to del f theta del theta 1 del f theta del theta 2. Right. So here if you see, this gradient will have component with corresponding to term A, and will have component corresponding to term B. So, sorry, not term B, I should say corresponding to term A and corresponding to term not A. So, these two possible cases are there, and let us do these two derivatives separately. So, one. This is partial derivative sign potential. Partial derivative with respect to theta a of e raised to alpha theta a phi. This thing I am writing in a bit separate. We are separating theta a out because the derivative. This is the variable. The other things are constant because this is a partial derivative. So b belongs to a and not small a is to alpha theta b. So the second term in the denominator is constant. So please be careful here. I may do calculation mistakes. If I do it, then please uh, rectify me. Write in the second step. Then alpha comes out and e raised times e raised to alpha a minus e raised to alpha theta a times the same thing. Sorry, alpha will come out again. So e raised to alpha theta a plus, yeah, plus nothing. So that is a constant. Uh, so that will be zero. Derivative will be zero. Fine. We have to do some simplification. So this term and uh, so if you take this, multiply this, the first term and the third term will be cancelled out. Hope I am right, right? So alpha times e raised to alpha theta a times b belongs to a e raised to alpha theta b by alpha a. Can you simplify this further? Any idea?
In the
Yeah.
lecture videos, they have done it slightly differently. They have taken a log, which simplifies this calculation.
Oh, okay. So is this Boltzmann parameterization done?
Yeah, I mean, they have called it softmax, not Boltzmann. But essentially, in the first step only, they take a log. Uh,
Okay.
they
So
make a definition in
yeah,
such a way that there is
I understood. So here, right?
yeah, they divide and multiply
Hmm.
by that finally, then you get the log of the gradient. Yeah, I mean, the gradient of the
Hmm.
log of pi data.
Right, right. Right. Yeah. So yeah, that is yeah, that I think will be easier, right? Okay, so now there is a chance of going back. So alpha by so
One question
this
here
term,
is,
if you see,
is the numerator does it correspond to the arm pulled at time t?
sorry, I cannot hear you properly.
So does the numerator correspond to the arm pulled at any given time in the expression for pi of theta?
Numerator, okay, so numerator is multiplication of two terms. So yeah, I'm coming to that. So let me write alpha theta a. If you separate these two things, uh, that will be. I'm not writing whatever inside that. And the same denominator. So a denominator is squared, so we are separating two things out. So if you see, this is alpha times. This is the probability with which you take action A when your policy parameter is theta. So this is pi theta A, and this is exactly what is the probability of not taking action A, right? So this is 1 minus pi theta A. Okay, so this is the gradient expression, and I think you can do now this uh, for delta the theta b, not b. Let me write a prime when e raised to alpha theta a summation. So find out this thing. I think this will be, it will take some help of. Okay, let me compute this because I need to code it anyway.
So
So
in the class, no, so whatever you have in the brackets over there, in the class they do a ln of that
yes, yes.
in the
So
lecture
yeah,
videos.
I have understood what you're telling. So what you're telling is this will be theta t plus, so you divide it by pi theta a and multiply it again by pi theta a. So
Yeah, and the approximation is summation of the current reward.
yeah, so I'm
Or
not going
anything.
to approximation now.
Okay.
Let it be. Yeah, so this is what it is, right?
Yeah, and that pi mu a, pi theta a, they have written it as Rn over 1 over n.
Mm. Please tell it again. I couldn't.
So that mu a, pi theta a, in practice, that is basically the way it is approximated is Rn
Yes.
divided by 1 over n. Right? That's the approximation. And then you just have to evaluate phi theta of log of phi theta. That's how, sorry, gradient of log phi theta. That's how they've done it in the class.
Right, right. Okay, so this let us compute it. So this is basically a by b plus x ddx. So, right. So this will be equals to minus to alpha a by then you have to take derivative of the uh, e to the power so, a prime e raised to alpha theta prime. So this will be equals to minus alpha times phi a times phi a prime. I hope I'm correct. So yeah, so that's it. Now how we will compute uh, this thing theta t update equation theta t plus 1 equals to theta t. So there are two cases, right? T plus alpha. So there are two. Mu a is also there. So this is not the actual update equation we'll use. This is the exact update equation if you knew the multi-arm bandwidth entirely. So mu a times alpha times phi a 1 minus and so sorry, I have messed up. This is not two cases. Let me expand this thing. Mu A1, where you are considering arm A1. So there, I'm saying considering that first term is A1. So the first term will be alpha pi A1 times 1 minus pi A1. So second term is A2, right? And which is not equals to A1. So the second term will come into picture minus alpha pi A2. But we are taking derivative with respect to A1. So, sorry, I think I have messed up. So this is gradient of theta, a gradient taken at theta t of pi theta t a1, right? And plus, say there are only two arms, mu a2 delta pi theta t pi theta t a2. Now let us write in vector form. There are only two terms. So theta t, we are evaluating at a1. So when it is at a1, this is the derivative with delta del a1. Sorry, my bad. Theta a1 pi theta t a1. And here it is delta theta a2. But we are this one is, and similarly a2 delta theta a1 pi theta t. So this is theta t a2 delta theta t a2 t. Sorry, 2. Yeah. Now let us replace all these partial derivatives with their what we have computed. Mu a alpha pi theta t a1 times 1 minus pi theta t a1. So what I suggest to you, you verify this calculation, this two gradient, I mean derivative calculation, using this log formulation also. This one. So I think they will be same, but still. This is alpha pi theta t a1 times pi theta t a2, right? That's what we have got here. And similarly, so this is mu a1 plus mu a2 times minus pi theta t a2. I'm writing a1 first. That's I think okay. T theta t a2. And here alpha pi theta t a2 1 minus pi theta t a1. Okay, so now we have the full update field. So let us write theta t1 here plus theta t1 plus 1 equals to theta t plus some vector. Now the thing is, you can do you cannot you do not have these things, two things. So in reinforced algorithm, you replace it by the current reward. Say at theta t, you have sampled arm 1. So arm 1 has given you reward RT. So at t, you know, actually here we have two options. Option 1, which is idea of reinforce, that at time t you have have you know at and rt. So what you do is update theta t plus 1 equals to theta t plus rt times indicator at equals to a. So if you choose arm 1, in this case, you'll choose this gradient. If you choose arm 2, you'll arm 1. If you choose arm 2, you'll choose this gradient. Not both of them together, and you will not know you can weigh them because you have only one sample. You are considering only one sample. Now, it turns out that you have more information at this time. So you don't have only one sample. You actually have collected lots of samples in past time steps, and you can actually use those. So instead of using mu a1, mu a2, you can just use the estimate of the those terms. So what you can do is option 2. Mm. Theta t1, theta t plus 1 equals to theta t plus summation mu hat t a delta theta pi theta theta t. And let us do some other things. Uh, I think you're also introduced to baselines, right? Can you please confirm? Yeah. So instead of taking this mu hat t, we can replace this. So I'm coming why we need to use baseline. That actually stabilizes our algorithm, stabilizes the parameter theta. So minus some r part D. I'm coming what R bar P is. So here there are two questions. Why do we need this is called bias T plus these two are not the same equation. So this is after adding bias. Why do we need to add bias? And second thing is uh, it why bias doesn't I should write in expectation. So we'll discuss all these things. Maybe we can just remove this in expectation. Okay, so my first question is why do you need to add bias? Can any one of you answer this? Okay, you think meanwhile let me write what R bar T is. So that is basically sum of all rewards from time 1 to time t minus 1. Okay, so let us answer the first question. Why do we need to add bias? If you see, say your reward range R T belongs to 0 to 1. So your mu hat T will also belong to 0 to 1. Now, if you are moving towards the uh, right point, it may happen, it will happen that your gradient is positive. It is very much likely that uh, you're always going up. So the entire term, this term will be positive. It is not necessary, but it can happen that all the terms are positive. And each round, each round you are adding this to theta t, and theta t is basically blowing up. And if you see in Boltzmann parameterization, we have already discussed this. Yeah, one thing is you take theta a star very large and others like finite. And another option, second option here is you take theta a star finite, but the other terms will be negative infinity. So both the way you can assign probability to a star near 1 and other arms near 0. So there are many possible parameterization which will give you optimal, near optimal performance. But what this, if you do not add bias, what will happen is this theta t will blow to infinity. So that's the main reason. So that's the reason we add bias. So I hope I'm just writing here numerical stability of the parameter iterates. Okay, now the second question is why bias doesn't affect. Um, So that will see it will not affect in expectation. What we need to understand that this bias is that doesn't depend on t, right? Or arm chosen at time. So it depends on t. Sorry, arm chosen at time t. So expectation at given policy by theta. Uh, we're seeing the expectation at RT. And what we're doing is if we are subtracting something by theta RT minus BT. BT is not a function of A. So RT is a function of A, right? So if we expand this expectation, this will be summation over A mu of A times pi theta of A minus BT. So here comes the thing. This BT doesn't depend on A. So BT times pi theta A. So what is the value? A belongs to A, mu A pi theta A. This is just BT, right? Because this pi theta is probability. Now, if you take gradient with respect to theta of this term, then BT is just a constant. So it doesn't affect. That's the reason. Sorry, I think this I should not write. So
But in that equation, that BT is outside the gradient.
sorry,
So the update equation,
just a
in
second.
the update equation,
Just a second, please. Yeah, tell me.
so in the update equation, that
Hmm.
BT is outside the gradient term.
So this, so you are, so when we are taking gradient, we are, this mu A is not a function of theta, right? So there we have shifted the gradient from outside the summation to inside the summation.
Okay. Okay.
No, so is it clear? Okay, let me explain this in writing.
So in the assignment also there is a question. I don't know if you have the access to the current assignment. Uh, there is a
Yeah,
question.
I have.
I think I'll tell you the question number. Question number 4 actually.
Yes, yes. Week 3, right?
Yeah, week 3, question 4.
So assignment or quiz? Which one?
Quiz, sorry. There is no assignment actually. This quizzes.
There is some practice assignment. Yeah,
Oh,
question 4. Okay. Yeah.
yeah.
That reinforcement. Yeah. Hmm. They're same basically. Okay. I'm giving the answer. Anyway, so this is the reason why they're same.
So, but
So,
if you take the expectation of the terms, the final. So, how are expected value of RT minus B and the gradient, and expected value of RT and the gradient? So, if you just they will be same only if the expected value of that derivative term is zero. No? If you take just evaluate the in the question in the final statement of that question, how are expected value of RT minus B derivative of the gradient, and how are expected value of RT and the gradient? They are related. So if you
okay,
just like expand it,
let me solve this. I'll, I think we can do that. Okay. Let me complete the writing here. Yes, it will be incomplete. Theta and is equals to 39 theta. Okay, so expectation of
we
RT
can't see a screen actually.
minus B. Yeah. Uh,
We,
what did
we
you
can't
say?
see a screen. We can't see a screen if you're trying to show the screen.
Oh, is it? Okay. I think it got unsure. Now we can see it.
Yeah, yeah.
And I prefer writing the subscript. Yeah. So summation over A, this is mu A time minus B times pi theta dA delta. So here I think it should be like technically it's fine, but theta t is not a random variable on which the expectation is taken. So theta, you can theta t is some constant parameter. Delta so this pi theta will come down, right? Pi theta a, theta t a, and this one is you can write 1 by pi theta t a. Still, Am I right?
Yeah.
A minus B. You can separately write these two things. Summation mu A delta by theta A. It's delta B you can write outside, and summation delta by theta A. Okay. I think I need not to say anymore, right? Do I?
Yeah, but so if they are equal, the second term is, how is that zero?
Yeah, that's what you need to figure out. Think it is very easy.
Because the derivative is involved, it is not very obvious why it should be zero.
Sum of derivative and derivative of sum are the same.
Oh, okay. So, got it. Makes sense now. Basically, it's the probability summing up to one, right?
Yes.
Okay, cool. Thanks.
Okay. So now I don't know whether I can finish coding of this algorithm. Let's see. Can you see the screen?
Yes.
No.
You share the notebooks actually when these notebooks.
Yeah. So you have the access to tutorial notes, right? I have shared in the same folder. There is a
Okay,
subfolder
thanks.
named, I think, code or something. Right?
Okay.
Okay. So write the function. So gradient based math. I'll be doing coding for the uh, second algorithm where we are replacing mu a by mu hat. We copy things from this. Delta is not needed. Uh, we have another parameter alpha, which is temperature parameter. So we can start our theta from theta from all zero, right? And we have k arms. Then from theta, we need to go to the distribution from where we uh, sample our actions. So let us call it pi. Pi equals to, I don't know how to write, NPXP uh, times theta by sum of let us write pi equals to this, and then pi equals to pi by sum of pi. So be careful. If I do any mistake, please rectify me. Then we need to sample. Sampling is, I think, there is a function already written. Oh, so numpy has a function. Sure. Yes. So this numpy random choice that is taking value from this first array. So this is basically 0 to k minus 1 array, and p is the probability. So we have a probability distribution on number of on the action set, and this function, inbuilt function in NumPy, is basically taking care of that step. Now we get reward at 80 and get here is the means. So this is where we are collecting the reward, and this is where we are summing up the reward and um, counting what is the number of plays we have already done. So the incremental update that we are not doing here, I think that is not much needed maybe. And so the step we are missing here is basically the update of theta. So let us update theta here after we get this R. So theta equals to theta plus something. So there are two vectors we have to multiply and then sum up. One vector is the uh, estimate of the mean. So estimate of the mean is basically sum of rewards by count, right? So I think we have already written that somewhere. See. NPTEL rewards plus, yeah, this one. So first vector is the estimate. So where here I'm dividing the reward. So this rewards vector is basically the mu hat. Okay. And then dividing it by counts and taking a maximum with 1 because otherwise it will give infinity. So that is one vector, and there is another vector which is the gradient, right? So the gradient, sorry, this one is a vector. Then the other one, every term is vector. Okay, so that is that I think will be going to be a bit difficult. Um, let's say delta, which is so delta is let us see what is the dimension of delta first. Uh, for each arm, there is a partial derivative, and the partial derivative is I mean delta by delta theta t a1 and ai, and we are taking partial derivative for pi theta t aj. So I above and j below, and both are arms. So delta will basically be a k cross k matrix, and so writing that delta is the main challenge, I think. Uh, Let us initialize this NP with zeros, and size is k cross k. Then let us write a for loop for I, two for loops, I in range k, and for j in range j. We have this delta I j, that is equals to so the diagonal elements will be of one type, and so range k, and the other elements will be of another type, right? That's what we got, because if I equals to I equals to j, then there is one formula, and if it is not, then there is another. So if I equals to, sorry, j, then delta ij equals to alpha times pi I, pi is, times 1 minus pi I. So 1 minus pi I. And otherwise, else delta ij equals to pi I minus alpha pi I times pi j, right? So I don't know if there is some nice formulation of doing this thing. There should be. So let me figure out if I'm doing the next step right. That is multiplying this rewards and yes, I think we have to do matrix multiplication. So there is a matrix delta. I know you cannot see what I'm writing, but yeah, yeah. Yeah. I think you can also verify this. This this will be matrix multiplication, matrix and vector. So at delta, comma this other vector. So first one is matrix, second one is a vector. So let us go through this code again, and if you see some bug, then spot it. So first things are initialization, that's fine. And then from t equals to 1 to 0 to n minus 1, it's running. Pi, the policy, which is exponential of alpha times theta. That's correct. Then we are normalizing that. That's also seems correct. Then AT is chosen using this random choice function where the probability of choosing arm I is pi I. That also seems correct. Then we are getting the reward from the environment by pulling arm AT. And also AR is basically the mean reward. Uh, so this is RT and this is mu of AT, right? And this delta we are initializing, then uh, we are uh, populating the values of gradient uh, by two for loops. States seems fine, but yeah, let's move on. Then we are updating the vector theta, and hopefully these steps are this things the last these things are most crucial, I think. If error occurs, it will occur here. Then we are summing up the reward and keeping the estimate counts, and this is regret we are calculating. Hope the things are fine. Then let us run this code and see what happens. Let's keep alpha equals to 1, run from the beginning. The same bandit instant. Oh, nice. It ran in the first time. Great. Satisfactory. So yeah, if you see this Thompson sampling is 20, fine. Uh, it is somewhere the 1,000 step performance is the cumulative regret is somewhere between 30 to 40 average. Here it is 20 above, so 25 around, I think, 23 around. Okay, great. So what we can do is now we can do average run. Let's do it. alpha. Yeah. Oh, this will also work. Call this function. Let's wait for some seconds. It's taking some time.
So one very high level question is, let's say you are running this
Yeah.
policy approach. Uh, at each time step, you come up, you have a certain policy, right, which gets updated every time. So you pull the arm as per the policy you have learned so far, right? And hope that
Yeah.
eventually it
Current.
converges to the. Uh, so what do you expect it to converge to? Some kind of a 1-0 kind of distribution, or like maybe
Yeah.
point 0.8, point 0.2 kind of distribution?
Yeah, so to converge to 1-0 kind of distribution, you have seen one, at least some of the parameters has to go to infinity, which is which will create numerical instability. So I mean, we are okay if it is like 0.95, 0.001 others.
Okay, okay. So one will clearly stand
So
out,
if
kind
you
of thing.
so recently the theoretical guarantee of this algorithm has come.
Hmm.
So they say that it will converge to, if some certain conditions are satisfied, then it will converge to this 0, what you are telling, the
So let's
degenerate
say there are
distribution.
just getting an intuitive feel. So let's say there are two arms which are very close to each other. They are not terribly different. So maybe one gives you an average reward of 55, another
Right.
gives you an average reward of 50, let's say.
Yeah,
Then it
here,
will
if
still
you see here, same thing.
uh, so
Arm
then
1
it will
and arm 8, I think.
so
Hmm.
at the end the policies will be will reflect that, or it will still be like 0.99 and 0.01.
It should reflect. But in like this analysis, theoretical analysis, there these are done for infinite. So they uh, assume that you are running this algorithm for infinity. That you will not never do in real life. So in real life, if you see this, if you print the theta, uh, you
Huh.
can do that. Then
No,
you
no,
will see.
even in ideal situation, let's say we run it to infinity, and the rewards are very close to each other. Say one arm on an average gives you Q star for one arm is, let's say, 51, and the Q star for other arm is 50. They're that close, let's say. So
Hmm.
what this algorithm converge to in the end? Uh, it should still say like with one
The
probability
degenerate,
peak.
the
Huh?
yes, yes, what you are telling, the degenerate distribution where A star is will take all probability and others will.
Yeah, 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 yeah. It should converge to that only, no?
Yeah.
Ideally.
Yeah. So if you see here, the theta is one at one place, it is very high. I think it is
Uh,
not performing so optimally. So fourth term is 7.394. Okay, that is the base term according to this algorithm so far. And if you see fourth term is what? Yeah, yeah, fourth term is not optimal. It is suboptimal. Okay.
okay, okay, okay,
So this is the finite time phenomenon. And
okay,
maybe if you run it for 1 lakh time steps, then perhaps it will take the right term.
okay, okay, okay.
Let us do that. I don't know how much time it will take. 10,000. Let us try it 10,000.
But the outcome should, in some sense, be always degenerate.
Yeah, so if you see here, one is taking more probability, and here the fourth term has reduced much.
Okay, okay.
This term has also very close to optimal reward, but yeah, it is still positive. These two are these two positive. These are yielding higher reward, close to optimal, so they are positive. The others are away, so they're negative, and this one is highest.
So there is also a couple of questions which I had doubt in the assignment.
Yes.
If you take question number 7, right? Uh, question quiz in quiz, there is a question number 7
Yeah,
where
let's assume full
uh,
RL problem. R full RL, okay. Taking according policy by that's here. Mhm.
so my question was, when you reach a state S, uh, you're still sampling the action. No, you're not. It's not deterministic. So once we have a policy, let's
So
say, yeah,
yeah, so this question is slightly tricky. So you can so they're saying you have a same you're applying a same policy for at time t and also t prime, and
huh,
in two times you have sampled two different actions.
huh, huh.
So is it possible on so non-stationary policy? It's of course possible because
Right, right,
non-stationary means that exactly that. But yeah, for randomized policy also it is possible where the policy is not necessarily non-stationary. It can be stationary. Stationary means your probability of sampling arm is same at every
right.
time.
So that's
So
what I wanted to ask actually. So even in the lecture, the professor mentions that you're always sampling an arm. It's not deterministic.
no,
So
so
it's stochastic.
it's very much contextual. So there are algorithms which does implies deterministic policy. So
Okay. So in some sense, you don't sample the arm. You always pick the highest arm.
yeah, something like that. Like UCB, if you see UCB, it's
Huh, huh.
choosing one particular arm always, right? The best arm according to that, which is maximizing
Right,
the
right,
UCB index. So
right.
that is sort of deterministic policy.
Right. Makes sense. And one more question in the assignment only was, I think it is, huh, uh, it is the fifth question. It is slightly tricky actually. The fifth question, uh, it is related to what we have done so far, the policy search algorithm.
Okay, policy search I'm not very confident with, so that this one I cannot help, I think. But still,
Okay.
let me read. What is alpha here? Okay, alpha
Alpha
is the
is the,
parameter
yeah,
of the algorithm. Yeah.
update rate.
Hmm. So in this family of algorithm, there is one alpha then and the beta, right?
Alpha beta is there.
So what is the value of beta, you think, in this
So,
update equation?
so it looks like when A equal to 80, no, they come out to be same, alpha equal to beta. But
Okay.
that option is not even there in the answer.
Okay.
But maybe I did it wrong. Maybe I'll redo it after, like, after the, let me just redo it and figure out. It's okay.
Yeah, sure.
If I have a question, I'll send an email.
Yeah, sure.
Okay. Thank you.
Yeah. Anyone else have any other question? Okay, so we couldn't do the coding of the value iteration for finite horizon. So in the next tutorial, we'll do this coding, and also by that time, you'll also be introduced with, I think, infinite horizon discounted Markov decision process. So that we'll go through, and perhaps we'll code the value iteration algorithm corresponding to the gamma discounted problem as well. Okay, so here we are stopping. See you in the next tutorial. Thank you.